session of Staff Cafe, and today we have a speaker of Isaac Ray, who is a third-year PhD student in our department. He's working with Dr. Song. He did his bachelor's in Texas A&M. He stayed in Texas A&M for Doctor of Philosophy and Statistics, thanks to Dr. Song. And he's done very cool research in Bayesian parametrics with very complex and correlated density functions. He's also very genius of C++ and dividing the code. So let's welcome Isaac and his research.
Thank you. Apparently, I'm the guinea pig for this microphone, so hopefully everyone can hear me. I can't speak as loud as I normally can yell because I have a bit of a mouth issue, and I decided that it's more important to not use oral anesthetic, so I'm not slurring my words as much. All right, so today I'm going to be presenting some work that I did with Dr. Song on the sort of alternative to a standard boosting algorithm that uses sort of a more flexible cut or a more flexible partition. One moment. Can't change the slides. Great. All right. So I'm going to start off with a little motivation, just sort of a quick data example for why we might care about solving this particular problem. So suppose that we're trying to, say, predict rent prices in, Sacramento, other than just saying that they're really expensive, right? So what we care about is the house prices or maybe the rental prices, and we have some covariates, such as, most importantly, the locations of where these things are. Any renter or realtor will tell you that it's location, location, location. And we also have some information about these sort of individual units. So we have maybe the square footage, how many bedrooms they have, how many bathrooms they have, things like that. And we know that the longitude and the latitude are very related to one another and also to the response, right? So it's really sort of unreasonable to treat them as being sort of these independent covariates when actually there's a lot of structure in between those two. And we can even see by plotting sort of on the log scale, the price here, based on the longitude and latitude, we have this sort of very non-convex, strange border that we want to be sort of mindful of because that'll have an effect on the pricing. And also, if we just try to make sort of cuts uniformly in either longitude or latitude, we're not going to get a very good sort of meaningful interpretation of what's happening with the price surface here. And more generally, we have some observed data, which I've indexed here with di, where every di has some covariance x and a response y, and that could be either some continuous thing, in case we're doing some sort of regression, or maybe some binary thing if we're trying to do some prediction like that. And so we have this p-dimensional feature vector that's lying in some feature space with some, we'll assume here, real valued response, and there's some unknown function, phi, that maps our feature space to our sort of realization of our response, y. And we'd like to learn something about this phi, knowing something a priori about the structure of our covariance x, right? So we know something about the relationships between our xj's, or maybe we have a hypothesis. Maybe we don't want to strictly say that we know something, but we just have sort of a loose intuition about something between our x's that might have an impact on learning this phi function. So a very popular approach for estimating phi is called ensemble modeling, right? So we've got our boosting methods, our bagging methods. There are others, model averaging, lots of different approaches where essentially we want to model our estimated phi, our phi hat, using, in this case, a sum of some sort of weak learner functions f. So we assume that we have capital K of these weak learner functions, each of which are contributing a little bit to our final estimated function phi. Stand by for technical difficulties again. One moment.
Okay.
Okay.
Remove it. Okay, hopefully it will go.
Okay. So as I was saying, so a very popular approach is using these sort of ensemble models, and most of us have heard of these things like XGBoost, random forest, light GBM, lots of very popular methods out there. So we're going to assume here that the form of our weak learner function is this decision tree, which I'm denoting here with a big T. And these decision trees have this nice recursive structure, which consists of nodes, which I'm calling here zeta, that define the decision tree structure. So there's decision nodes and then there's leaf nodes, where a decision node is a predicate or just sort of a true or false function that sort of asks a question about our feature space, mathcal_x, and says either it's true or false. So here I was saying it's mapping to either 0 or 1. And each one of these decision nodes has exactly 2 child nodes, which I'm just denoting with zeta t and f. And so these child nodes could either be another decision node or they could be a leaf node, in which case the leaf node has no children. So then we can evaluate a decision node as sort of the predicate times the left leaf or the left child node plus sort of the inverse of the predicate times the other child node. So this is the sort of formal math notation of saying at every step in this decision tree, we make a decision and then follow that path. And then we do the same thing over and over until eventually we reach a leaf node. And these leaf nodes take a fixed scalar value, which we call the leaf weight. And in order to sort of use our decision tree to evaluate or predict a new location, we pass in the covariates, we recursively evaluate down this decision tree, and then we take the final leaf node that we arrive at, we take its leaf weight and make that as our predicted value. So in this talk, I'm going to focus on boosting rather than bagging. We have investigated a little bit with the bagging, and there's sort of some promising directions there, but I don't have any concrete results to share with you today. So gradient boosting is a technique in which, in order to grow or choose how we structure our predicates, we take the gradient of some loss function with respect to the data we observe in order to find what the sort of optimal loss is at every step. And we'll do this over and over until we reach some kind of stopping criteria. So given some loss function, which I've denoted here as L of sort of the prediction yi hat and our observation yi, we take the gradient and then use that to inform our update of our weak learner or a particular weak learner, f little k. And then over time, we're shrinking that contribution or the learning rate to make sure that no one weak learner is actually being too strongly informative. And unlike bagging, instead of updating all of our weak learners at once, we'll update our weak learners conditioned on all the other weak learners, or sort of this backfitting, this residual fitting. So at every step, we look at what is the current error and what is the optimal choice in order to minimize our current error. And we keep doing that until we reach some sort of threshold as to the error being low enough or maybe the penalty being too high. And in order to sort of do these updates, we're only going to consider sort of these growth steps where we take a leaf node and turn it into a decision node, which itself has 2 more leaf nodes. And the main sort of focus on this work that's different from the other gradient boosted decision tree models is that existing methods use this predicate where we look at some specific single covariate and ask whether or not it's greater than a fixed scalar value C for one feature xj and one constant C. And this is sort of the restriction that we're trying to lift with this work. So before I talk about what we've done, I'd like to review sort of a very popular method called extreme gradient boosting or XGBoost. Probably most of us have heard of Kaggle. XGBoost is sort of the end all be all, or at least the sort of out of the box state of the art method that everyone likes to use. And the way that it works is that it's extreme gradient boosting because it takes both a first and second order derivative, right? And the nice thing is we have some nice closed forms for these in most cases. And as a technical detail, as long as our loss function is sort of roughly quadratic, then we can evaluate these gradients in closed form. If they're not, we can always do sort of a second order Taylor approximation and do something like numerical gradients in order to estimate it. But for now, we'll just focus on mean squared error because it has these nice analytical solutions. So at a given iteration t, when we're updating our weak learner f sub k, we have the first order gradient information gi and the second order gradient information hi. And these are actually very fast to compute. I won't go into the sort of details of what these expressions are, but safe to say that they're sort of effectively constant time. We can evaluate them extremely quickly. And then we'd like to sort of write this penalized objective function as the second order Taylor expansion around our current step, LT, where, so we take for all the different data points, we look at the loss plus the current estimate times the first order gradient plus 1/2 second order gradient times our estimate squared plus some penalty big omega of fk. And generally that big omega is going to be penalizing both the depth of the tree and also sort of how large the leaf weights are, just to make sure that we're not doing sort of overfitting to our data.
Ask if you apply this to the spatial data or the spatial temporal data.
We focus mostly on spatial data. However, we do have an idea for how this can be applied to spatiotemporal data, and I'll get to that in a little bit. And so the sort of big trick that XGBoost uses, and the reason it's so fast and so popular, is that we can, in advance, sort every feature in ascending order, and then just do a linear scan over all of our observations and greedily choose sort of the best predicate, or really the best C and the best XJ, in order to grow our decision tree at every step. And so minimizing that loss is equivalent to maximizing this expression for the gain, which is sort of 1/2 the gain of the one half the gain of sort of what would happen if we made the new predicate on one side, what would happen on the other side, if the leaf node was true or if it was false, minus whatever the gain would be if we just chose not to split there, plus some penalty gamma. So I'm going to do a little graphical example here. So let's assume that this is our data, right? So we have 4 observations, DI from 1 to 4, and we have 3 covariates, X1, X2, and X3. And I've written it here where each one of these is ordered in order of the particular covariance, right? So this is the observation sorted in order of X1, in order of X2, and in order of X3, where the first one is the index of the data, the second one is the index of the covariate, right? So whenever we start, we have sort of this blank weak learner, this null weak learner, where all it is a single leaf node, which I've just drawn as this black square, that every observation maps to. So every observation maps to this leaf node, which generally is initialized as something like 0, just so it's uninformative. And what we want to do is over all this set of possible splits, all of these different sort of arrows here, we want to choose the one that best separates the data based on that gain function from before. So we search over each one of these, each one of these, and each one of these. And the nice thing is, because that we've bordered them already, we can do this linear scan and then just do sort of this message passing, where at each step we're only changing one term of that gradient calculation. So we don't even have to compute it every time. We just compute sort of based on it, what is it for this node versus all of these, and then sort of subtract this term from this side and add it to this side, and do the same as we go along. So it makes it even faster to evaluate that gradient. And so suppose the best choice here, the one that maximizes our gain, is splitting right here. So our new predicate is X1 greater than the value of our second observation, its first covariate and the second observation. And if a observation satisfies that, so our third and fourth one do, it evaluates the true, and now we map it to this blue color. And otherwise it evaluates the false, and we map it to this yellow color. So this is sort of our first iteration. So we've grown the decision tree once. So now, whenever we go to grow the decision tree again, we want to do the same procedure, but over each existing leaf node. And across all the different leaf nodes, again, choose the optimal one in this greedy search fashion, right? So now our set of possible splits is conditioned on this leaf node, right? So we can actually ignore both of these because they don't contain any of the data that's in our current leaf node. We can ignore this and both of these. Essentially, making splits across any of these would not actually help us at all in splitting up D3 and D4. So we don't even have to evaluate them. We can just skip over them because we know that it's not going to give us any gain. So we only have to evaluate this one, and this one, right? So by conditioning on sort of this leaf node, our search space has diminished substantially. However, we do also have to repeat the same procedure for the yellow node. So then once we've conditioned on this blue node, suppose we choose this one to separate the third and fourth observation. And now we have sort of, well, we'll assume that whenever searched over the yellow nodes, it didn't find any positive gain. So we say that we're done. There's no more gain to be had. This is the optimal split. And so what we have is that the fourth observation sort of follows the true predicate both times. The fourth one follows true then false. And both the first and second are false at the first predicate. And we can visualize this as sort of the codomain of this weak learner function f, right? So we start out, and here's our D1, D2, D3, D4 plotted against its covariate values for X1 and X2. So at our first step, everything is mapped to the same response value, which is just black. Then after our first step, we sort of draw this line here, and we've split up our feature space in this axis parallel way along perpendicular to x1, where if its value for x1 is greater than the value for the first covariate in D2, then it falls into the blue, and otherwise it falls into the yellow. And then once again, so conditioned on this blue node, then whenever we're making this orange split, the reason that it doesn't go all the way across here is because we've conditioned, right? So we're only considering data that's sort of already satisfied this predicate. So now we split this here. And so D3 satisfies both, D4 only satisfies the first. So now we have this sort of rectangular region for D4, this one for D3, and this one that contains D1 and D2. And we proceed until we've sort of ceased to have any gain, right? So we can no longer learn anything else from this data. Okay, so now everyone is very familiar with XGBoost. So now we're going to talk about the new development. So before we can talk about a sort of graph split-based predicate, we have to describe what we're talking about with graphs. So what we do is we assume that for every weak learner, we have a set of so-called candidate graphs, which I'm noting here as sort of this GK. And we allow the set of candidate graphs to vary across weak learners. So different weak learners can have different candidate graph sets. That's fine. And we define a candidate graph, so just a member of our candidate graph set, as being a graph with an arborescent structure. And I'll show you a picture in a second. But an arborescence is like a directed tree is really the main restriction. So it has to be a tree. It needs to connect all the elements. It needs to have no cycles. And the number of edges should be the number of edges should be 1 minus the number of nodes. And it needs to be directed in such a way that starting from one particular root node, every other node is reachable. Here we go. So I have here 3 examples. So this is just a graph, right? So we have some nodes, we have some edges that are connecting our nodes, and this is not an arborescence. It's not directed, it's not a tree, it doesn't satisfy anything we need. Here, we've caused it to be directed, so we've removed a couple edges, it's now directed, so now we have a nice DAG, but it's still not a tree, right? Because this node is reachable in 2 different ways. So if we assume that this is our root node, so I've made the root node a little bit thicker here, every node needs to be reachable from the directed edges, but only in one way, right? It has to have that tree structure and be directed. And the reason that we want to restrict ourselves to these arborescences is because of these 2 properties. So the first one is that by starting at the root vertex, we can actually define an ordering on the graph. And essentially, we can just do a topological sort. It's the easiest thing to do. We steal that from computer science. Now we have a nice order on our graph in order to sort of just define algorithmically how to do our search. And the second thing, which is really more crucial, is that these arborescences are sort of split separable or sort of closed under graph splits, right? So if you remove any edge from an arborescence, the 2 subgraphs that remain are also both arborescences. So you sort of can't escape the set of arborescences by just removing edges. So we're guaranteed that we can sort of keep this recursive algorithm and never end up with a data structure that we don't know how to handle. And this parallels this sort of left and right or true and false predicate set from XGBoost. And we're going to use that information. Right, so if we imagine no matter which one of these edges we remove, what we end up with is 2 subgraphs which both satisfy this arborescence structure. So if you remove this one, this is the original root node. Now this is a new root node. So we have this arborescence and this arborescence. And no matter which edge you choose, you'll always end up with that structure. And suppose we remove this edge right here, we'll end up with this arborescence here, and this one, which is actually sort of a special structure we call a chain graph, where every parent node has exactly 1 child node, except for a leaf, which has no children. Okay, so I gave you a motivation with some data, and now I'm talking to you about graphs, and this probably seems really out of nowhere. So before I can tell you about what the graphs have to do with our data, right now I'm just going to say, suppose that we have a candidate graph, right? So we have something that's an arborescence and it lives in our candidate graph set. And we assume, this is a key assumption, that we have a known function, sort of ZQ, that maps from our feature space to the vertices of our candidate graph. And we call this the binning function. So essentially, given any set of covariates, we can map that set of covariates into one of the nodes of our candidate graph. Now, there's sort of a subtle point here. it is possible that ZQ not be able to map every possible set of covariates. Under certain restrictions, that's allowable, but it does restrict you to doing only transductive inference, where you have to have your testing data at the same time that you're training your model. So here, we want to make this as broad as possible, so we say that we have to have this Z function, this binning function, satisfy the property that we can map any covariate or any set of covariates that lies in the feature space. Yeah. So Q is sort of the index of the candidate graphs in the candidate graph set. So for a candidate graph, calling it sort of this directed gamma Q, we have to have a binning function ZQ that can map any covariate to the set of vertices in our directed gamma Q. Directed because it's a arborescence. And sort of the key feature here is that we allow our binning function to be sort of an arbitrary function of multiple features in X. So that way, we're not making these axis parallel splits anymore, because a candidate split, sort of these splits that define our decision tree, can be defined in terms of multiple features instead of just one. And we also sort of make this assumption that this ZQ can also be defined such that multiple observations are assigned to one vertex, right? So it doesn't have to be one-to-one. It can be the case where there are many fewer vertices than there are observations. And that's another way to get sort of these computational savings. That's actually the reason why we call it a binning function, because we can treat each vertex as being sort of a bin of data rather than a single data point. And by doing that, we can speed up these gradient calculations by searching over fewer possible splits. Okay, so now I've just told you about binning functions and graphs, and I haven't actually told you how we actually do any of these things, right? So choosing a ZQ and a candidate graph generally have to happen at the same time, because probably they're related. The structure of the candidate graph is probably going to inform sort of how your binning function chooses to map observations into itself, or into the candidate graph. So for univariate data, we can construct our candidate graph to be a chain graph, like I mentioned before. So there's a root, and it just has sort of a set where every node points to the next node until the final leaf node, which has no children. And that's it. That's the entire structure. And the nice thing about this is by choosing our binning function to order the data and then map it into these vertices, if we choose the number of vertices to be equal to the amount of data we have, we've exactly recovered XGBoost, right? So if you imagine, back to this picture here, each one of these you could treat as being a chain graph, right? So our binning function is sorting them by the particular covariate. Our candidate graph is sort of the structure where we have the same number of vertices as we have observations, and we just map each one in order, and we recover exactly the same thing that XGBoost does. But we can do more than just that. For example, we can do histogram style binning, like LightGBM does, which is sort of a modified form of XGBoost. And the benefit of that is that we can reduce our computation by essentially treating every vertex as a bin of data where we only search between these bins. So we cluster things in advance and say, we kind of already know that all these things belong together, at least in this particular candidate graph, and we don't need to do searches for splits that separate them. And for data, for example, that lie on some known manifold, we can sample these random tessellations, which I'll show a picture of in a second, and then use those tessellations to draw a neighbor graph where every polygon has an edge connecting it with its neighbors, and then sample candidate graphs or sample random spanning trees from that sort of fully connected graph in order to generate our candidates. And of course, if our data already has a graphical structure, things like citation networks, we can just directly sample candidate graphs, or we can sort of collapse the graph using some kind of greedy community detection algorithm. And of course, there's more choices than just these. So there's sort of a lot of unexplored choices for how we can choose our candidate graphs and how we can choose our binning functions for mapping our observations into those candidate graphs. But in the most general setting, a candidate graph is expressing some hypothesis about your data, right? So if you have these chain graphs, your sort of hypothesis you're expressing is that these observations only relate to each other within a given covariate. Or you can have something more complicated than that, where your set of possible splits relates multiple covariates. Okay, so here's an example where we have some known manifolds. I'm assuming we know that our data lies on this strange rotated U shape. So the first thing we do is we generate all of these random polygons. This is a random Voronoi tessellation. Then, if you ignore the color, we imagine that every polygon we can represent with a node, and we connect every node with its neighbors that share an edge, right? So you can imagine this polygon right here shares an edge with this one right here. So we draw an edge between them in our sort of neighborhood graph. Then from this connected graph, which is not an arborescence, right? It's not a tree, it's not directed, but we can randomly sample spanning trees from this. There's a couple different algorithms for doing that. And then based on the spanning tree, we can arbitrarily choose one of these to be the root node. And from there, it sort of forces the rest of the graph to be directed. We just start from the root node and recursively go down and make everything point outwards from it. Yeah.
So you're saying in the second graph, the nodes or the dots correspond to polygons in the first graph.
Yes.
How is it like a centroid of each polygon, or?
The way that I plotted it, it's the centroid, but in principle, you don't need any sort of graph embedding in order to actually do this algorithm. That's sort of the thing, is we don't want to operate in this Euclidean space. We want to operate in the graph space, which is sort of this more general framework. So for plotting purposes, yeah, I chose the centroids. But more generally, you could imagine that this node represents the entire polygon, not a particular point within it. Okay. So now we have a candidate graph and we have a binning function. And so now we can define sort of our new predicate that sort of drives this entire work. So a graph split decision rule is a predicate that uniquely is identified by an edge in a candidate graph, where for any vertex, it's true if removing the edge causes it to belong to one subarborescence. And so we denote it as this, we split at this edge, right? So by splitting at this edge, for every vertex in the original arborescence, either it belongs to the first subgraph that had the original root node, or it belongs to the second subgraph that has sort of the new root node that's obtained from removing one edge. So we have our predicate, and we know how to map our data into our graph, into our vertices. So now we get the exact same sort of left and right or true and false parts of our gain, right? So for any observation, we can evaluate whether or not it belongs to the sort of true part of our predicate or the false part, and we can do the same recursive evaluation in order to get that predicted value. So now we can proceed almost exactly like XGBoost with just a few caveats. So I'm going to show sort of the same example as before, right? So in this case, I'm just supposing that we have two candidate graphs. So here's our set of candidate graphs, sort of big G, and we have our first candidate graph and our second candidate graph. And our first candidate graph is actually laid out in the same way that our XGBoost one was, right? So we have a chain graph where our root node is here, and these are actually ordered in increasing order. Right. So we're doing the exact same thing. So making a split in our first candidate graph is equivalent to the same algorithm being taking place in XGBoost. But for the second candidate graph, I show sort of a more flexible arborescence, right? So in this case, I'm actually not even requiring that the binning function assign any observations to any particular bin. It's perfectly fine that there be bins that contain no data. And you'll actually end up with that happening pretty frequently if you do this random tessellation strategy. So from here, we can immediately just not really consider these vertices that have no data, because we know that splitting between two vertices that have no data is going to result in no gain. There's nothing to be gained from making a split that doesn't change anything about our observations. So the only things that we need to consider is this node, which contains both the first and third observation, this one containing the second observation, and this one containing the fourth observation. And we start from the same set that we did with XGBoost, where we have this empty weak learner that has no splits. So to start with, we do exactly the same thing as XGBoost. We find that this is the split that gives us the optimal gain, right? So now we have two arborescences. So we have this original one that contains D1 and D2 based on this original root node. And then in this dashed node, we have a new root for this arborescence that just contains V13 and V14. And so our predicate is that we split on edge 1, 3, which is this one right here. And if it belongs to that new, arborescence that's rooted at V13, then it goes to this side of the decision tree. Otherwise, it goes to this part of the decision tree. And so far, we've done exactly the same thing that XGBoost done, but in a way more complicated way. Hooray, right? But we're not done. So once again, I've conditioned sort of, I'm assuming that we're going to consider this leaf node here. And now in the second graph, in the second candidate graph, we no longer need to consider the contribution of D1 because D1 does not belong once we've conditioned on this sort of blue leaf node here, right? So now we only need to consider splits that can separate D3 and D4. And so the possible splits are this one, and this one. And all of those splits we can just ignore because they won't tell us anything about our data, conditional on it having already been split out here. So say now we remove this edge, we've separated out D4. So now we have this decision tree. Again, in principle, you would have to evaluate this both at the yellow, and then after evaluating it at both the blue and the yellow, we then evaluated all three of these, right? But here, we'll just say that this is sufficient. We have sufficient gain here. There's no more gain to be had, and this is our final output. But the key assumption here is that these V's actually make no assumptions about this covariate structure in X1 or X2 or X3, right? Depending on our binning function, these V's could represent any number of different relationships in our data. It's entirely up to us how we construct these graphs and how we choose our binning function that will define sort of how meaningful these splits are. But in principle, this split could represent a highly multivariate split, something nonlinear. Just to sort of illustrate that. So using just the same two splits, right? So I've done the same thing. So we have our first split here, our red, and then conditioned on our red, we've made our orange split here, and we have now our three groups. And you can see the partition that we end up with has nothing to do with any axis, right? And to even demonstrate this, I've rotated this by 45 degrees to show that in order to achieve this sort of 45-degree line partition, you would actually need many splits if you're doing axis parallel things, because axis parallel splits are very bad at approximating these sort of multivariate decision thresholds. Okay. So now we've gotten through lots of not particularly interesting theory. Let's talk about data analysis. Okay, so how do we do this? I implemented this in C++ using OpenMP for parallelism. Both a coarse and fine grain parallelism option are available, but I can tell you the coarse grain one works much better in practice. And then we wrote an interface to R just so they'd be directly comparable with the other methods being implemented in R. So of course we compared against XGBoost and Random Forest, which are the two most popular ensemble decision tree models. We also compared against BART because we like GetGeorge, and his package is pretty cool. We investigated other approaches, things like oblique tree ensembles, which are essentially a slightly multivariate version of a normal random tree or random forest algorithm. However, most of the implementations left a lot to be desired, which is to say we couldn't get them to run without crashing. And also, we know sort of from a theory perspective that oblique tree ensembles are not going to perform as well as ours does, just because it's a slightly more restrictive structure. They sort of rely on these linear combinations. And in order to do sort of like cross-validation, which is very important for these ensemble models, we use the correct package. It is worth noting, actually, we did not do any cross-validation for our method. Our method uses the exact same set of hyperparameters for every data set, whereas the XGBoost and Random Forest models did some rather extensive hyperparameter tuning, just to make sure that we're giving them a fair shot. And it doesn't matter. We beat them anyway. So this is on some sort of synthetic data, so that U-shape that I showed you before, and I'll give you a picture in one slide from now, and also a torus, which is sort of a three-dimensional thing. So the U-shape is sort of a manifold that is really sort of a one-dimensional, which is just sort of your coordinate along that curve. That's in 2D. The torus is sort of something that is observed in 3 dimensions, but really is only 2 dimensions. And we did both regression and classification performance, so everything I've assumed up to here is that we're doing regression, but of course, we can just as easily swap out the loss function for something like a cross entropy instead of a mean squared error and do classification instead of regression. So we win. All right. So for things like the U-shape, which sort of have these, kind of aggressively bad performance for axis parallel splits because of its, 45-degree angle alignment, of course, we really just crush everyone. Even after hyperparameter tuning and in some cases letting these things run for hours, they can't compete. Now, in other cases, they get pretty close. So the classification surface that we chose as our testing function was relatively simple and actually did have fairly axis-aligned boundaries. And you can see that the performance sort of bears that out, right? They perform relatively similarly even across 100 replications. But we do still slightly edge them out just because, you know, more choices for the optimal gain gives us more flexibility in expressing what our estimated function can look like. So here is the U-shaped regression example. So I've got the sort of true value here. So this is the truth. And you can see we have this circle, right? And then we have something that looks roughly like a Gaussian process. It is a Gaussian process. So we simulate one of these, and then we simulate about 1,000 or so observations from it, and we fit all these different models. And one thing to observe is our method, we can achieve this sort of nice curve, right? So we can actually capture some of this circle. And that's really where we get most of our savings. And when you sort of compare that to things like BART, random forest XGBoost, which are all using this univariate axis-aligned decision boundary, you always end up with these sort of axis parallel artifacts. And this is really what's hurting their performance, right? So we have these nice, beautiful straight lines that don't match the true function at all. I believe I left it out of this particular set of slides, but if you plot the error surface, you can really see that on the boundary and at these sort of discontinuities in the true function is where the performance really suffers for the axis parallel methods.
How many is a solution? Like, does it, like, what depends on initialization? Because
you say-
can you get the like very different partitions depending on.
Yes, so something that I sort of skimmed over, the reason that we allow different weak learners to have different candidate graph sets is because you can actually sample many of these candidate graphs. So for example, we can sample one tessellation. From that one tessellation, we get one neighbor graph. But from that one neighbor graph, we can sample, for example, 5 candidate graphs that sort of have different connection properties across the different polygons. However, in a different weak learner, we could sample a different tessellation. And those, in that tessellation, sample 5 new candidate graphs. So we can generate sort of arbitrarily many of these sort of like very weak hypotheses about how the spatial information is being encoded. It's just the additive form. So at any point, you can plug it in, evaluate the decision tree, and then you add up the sum of the different weak learners in order to get your final estimate. But if you imagine, in some sense, you're actually taking the intersection of all of these different random tessellations. So you end up with these extremely fine polygons, but you don't actually have to work with a tessellation that has 1 million polygons, which would be very expensive. Okay. So here's some real data. Some of these are things off of UCI machine learning data sets. Other ones are just common spatial data sets. Core and PubMed are citation graphs. So these are things where the graph is actually known a priori, and all we have to do is sample candidates from it. The rest of these, we did the random tessellation strategy using Voronoi tessellation. And if it's denoted with an R, it's a regression task and showing sort of the mean square prediction error. Otherwise, it's a classification task and it's showing testing accuracy. So overall, we win again. Hooray. Not always as well as we did in the sort of toy example, which of course we constructed to be very beneficial to our method. And in some cases, we actually did not win. So for example, the Las Rosas crops, this data actually is relatively well axis aligned. It's almost like the true function looks as if it's sort of the response function from one of these axis parallel methods because it's so rectangular. And so of course, with things like hyperparameter tuning, you know, some of random forest in particular was able to beat us out. But in general, we do still get quite a bit of gain here. And again, with no real tuning being going on here. I will say it may not be clear how we fed these citation graphs into the sort of methods that don't handle graphs. So what we did is we looked at different projections into Euclidean space. And essentially, we just took the best one. We tried to give them the best possible shot, depending on like how many dimensions we wanted to project the graphs into. We did also look at doing sort of a active manifold learning style embedding where we did like a UMAP or a PACMAP algorithm in order to try to force these things into a Euclidean space that may be more beneficial, but we still beat them in those cases too. Okay, so back to our original motivating example, our Sacramento housing data. So essentially I've fixed the covariates besides the longitude and latitude at their medians, and just plotted sort of the predicted price surface across space. And you can see we have this really nice, smooth prediction surface that highlights sort of these nice things like this area right here is downtown. You can see it's got this higher price. The higher price line actually kind of follows this highway right here, which is actually sort of a thing that's known to be true about Sacramento. Essentially, there's a little bit of redlining going here where sort of what people classify as neighborhood quality drops off rather substantially. And even though it follows this sort of curvature, we're still able to capture it. And when you compare that with the predictions from BART and XGBoost and Random Forest, you end up with lots and lots of these sort of axis-aligned artifacts that don't really have any meaningful interpretation. So to wrap it up, just in time. XGBoost, it's a very flexible extension of a standard graph gradient-based decision tree model. It has lots of applications to things that have sort of these pre-existing prior relationships, so spatial covariates, potentially time covariates. You can imagine a temporal graph looking like a chain graph, of course, and do essentially like a change point analysis by evaluating those splits. We still get all the benefits of standard gradient-based decision trees, so it's fast, it's scalable, it's very easy to deploy. You get importance, like variable importance scores, which in this case, you sort of get those per candidate graph, but depending on how you did your binning function, if it's invertible, you can sort of translate those into individual feature importances. And we are able to have all that, as well as having these sort of much more flexible decision trees. And there's lots of future directions. So I mentioned earlier, you can, of course, use manifold estimation techniques like UMAP to do sort of these embeddings into Euclidean space for sort of the benefit of the competing methods. However, most of these methods actually sort of do what they do by first estimating a weighted graph that defines feature relationships. And we can just directly take that weighted graph and sample candidate graphs from it and then use it ourselves without having to do any embedding, without losing any information. Of course, there's lots of different loss functions. I focused here on mean squared error for regression and cross entropy for classification, but there's plenty of other ones that are out there. If you're interested, you can essentially look at the XGBoost list of loss functions that they support. We can use the same ones because we're doing essentially the same thing. There's also various data augmentation schemes. So for example, one popular method for density or intensity estimation is using a so-called logistic approximation, where you sample from a known field, treat those sort of dummy points as a 0-1 binary classification problem, and then use those to estimate the proportion of true points as your density estimate. Of course, incorporating time series data, there are better ways than just using a chain graph, but that's sort of the most straightforward one. We're looking at sort of some alternatives for doing the spatiotemporal sort of combined correlations. And of course, there's backing instead of boosting, which actually at this point we have tried, and it does work quite well. It just has some sort of different caveats to the boosting approach. And that's it. Yeah.
So you compared your method to different, as a method that have a linear split.
Yeah.
But have you compared to methods that has non-convex split? And how was your algorithm performing?
Yeah, so there's not a lot of methods that do sort of nonlinear splits. So oblique decision trees is sort of the most popular one in the past. The one that we could eventually get to run without crashing, it doesn't compare. It does, very marginally better than standard random forest, but not as well as our method. And it takes substantially longer to run. There is, of course, a strategy where you can actually generate random linear combinations of your variables and treat those as augmented features to feed into these as standard boosting and bagging algorithms. But in practice, you need to do that for sort of a tremendous number of combinations, and it doesn't scale with your number of parameters very well.
Back to that Sacramento.
This one?
So you gave exactly. You gave the highway explanation for why there's blue there, but maybe I'm thinking far away. Is there like a blue separation between those yellow blobs and north?
Yeah, so right here, there is a little bit of like it almost looks like a tightening, like this little blue belt around the thing. So that's actually the exact location of the highway. Okay. So essentially, the penalization is causing the response surface to be a little lower there because we have no data that's on the highway because there's no houses on the highway, hopefully.
That's cool. Your method with that.
Really, no. Just sort of the nature of these axis parallel splits, it really can't capture something like this highway without sort of wasting many of its I say wasting kind of with air quotations here, but it would have to spend many splits in order to capture this. But in doing so, it's going to sort of increase how much it's overfitting to the data. And after optimizing, you know, the hyperparameters, it finds that that depth is not going to give the best accuracy.
Very much again.